Спасибо большое за приглашение. So thank you very much for the invitation. So I will talk about Rotas Basis conjecture, which is a problem in Metroid theory. So Metroids, they're general objects which generalize things like independent sets in vector spaces or acyclic subsets of graphs. And to motivate Rotas Basis conjecture, just before giving you a definition of a Metroid, I'll give you a couple of examples of things it implies in other settings. So here's a very kind of natural and simple question about simplices in a real space. So say you have a real vector space and you have a collection of n simplices. So for example, for n equals to 3, we're looking at R2, and you have triangles, and you have 3 triangles in R2. And you think of every triangle as having a color, so red, green, and blue, and we really care about the corners of the triangles rather than their interiors. The question, how many rainbow triangles can you find in this setting? So rainbow triangle is one which uses a corner from each of the original triangles. So throughout the talk, there'll always be kind of original objects like these original triangles where each one has a color, and we'll be looking at rainbow objects. So in this case, you can find 3 rainbow triangles, and they're disjoint. And in general, a special case of Rotas conjectures, you can find n in Rn minus 1 like this. So that's one example. Here's a second one, which is where the name Rotas Basis conjecture comes from. If you have bases in, again, real vector space, so n bases in Rn, so for example, basis 1, basis 2, basis 3 in R3, the standard basis, and 2 other bases, how many disjoint rainbow bases can you find? Again, a rainbow basis is one which uses a vector from each of the original bases. Again, the conjectures, you can find n of them. So we should be able to find 3 here. And the 3 you have here are just the rows of how I've drawn it. So this vector, this vector, this vector, they're independent similarly. These 3 are bases and these 3 are bases. So this is the original formulation of Rotas Basis conjecture, that if you have n bases in a vector space, you can find n disjoint rainbow bases. And later Rota generalized the conjecture to Metroids. And a final example, which is graph theoretic, and this one will be important because when I talk about a bit about proofs later on, I'll be kind of giving you examples in this setting. If you have n spanning trees on n plus 1 vertices, how many disjoint rainbow spanning trees can you find? So for example, here you have the n equals 4 example of this. So you have 4 spanning trees on 5 vertices. So for example, you can see the red forms a tree, the green forms a tree, and the blue and the light blue also form trees. And we're looking for disjoint rainbow spanning trees, meaning spanning trees which use all different colors from the original trees and don't repeat edges. So we'll always be looking at multigraphs, and when we say don't repeat edges, it just means you don't use the same edge and the same color. So for example, this tree and this tree, they use kind of this edge twice, but in different colors. And again, the conjecture is that you can always do n of them. So now I'll explain what Rotas Basis conjecture is and how it's, or what a Metroid is, and how you can use the language of Metroids to generalize these 3 settings. So Metroid, so the abstract definition is a Metroid on a ground set V. So whenever we talk about Metroid, you have a ground set on which the Metroid lives. It's a family of subsets of V. So it's a subset of the power set of V, or you could also think of a Metroid as a non-uniform hypergraph. So it's at a very basic level, it's a hypergraph with some additional properties. The kind of hyperedges, or the elements of the Metroid, they're called independent sets. So instead of hyperedges, we say independent sets. And it has 2 properties. One is a very simple property that it's downwards closed, meaning that if you have an element in the Metroid, if you have an independent set, then every subset of it is also in the Metroid. Every subset of an independent set is independent. And secondly, something called the augmentation property, which is what really makes the Metroid a Metroid. It says that if you have two independent sets of different sizes, then you can always move an element from the bigger independent set to the smaller one to get another independent set. So this is what makes a Metroid a Metroid. And thinking back to the previous example, the first one you should notice that is a Metroid is the vector space example. So if you look at the family of independent sets in a vector space, then this forms a Metroid. And that's really where all of this terminology comes from. That's why these things are called independent sets. So let's just remember this. If you have an independent set in a vector space, every subset of it is still going to be independent. And secondly, if you have two independent sets of different sizes, then you can move an element from the bigger independent set to the smaller one to get a new independent set. So the triangle example on the first slide is similar. What about this tree example? What's the Metroid here? So how it works is something called a graphic Metroid, where if you have a graph, you can construct a graphic Metroid whose ground set, the ground set of the graphic matrix will be the set of edges in this graph. So the Metroid will be set of subsets of edges of this graph, meaning subgraphs of this graph. And the set of independent sets is the set of all acyclic subsets of this graph. So all forests contained in this graph. Here I've drawn all the forests which are contained in this. They have different number of edges. So here you'll have some with 2 edges, you'll have some with 1 edge, and there's one forest which has 0 edges. Let's check that this forms a Metroid. You need to check that it's downwards closed. So the subset of a forest is a forest, yes. And secondly, you need to check that if you have 2 forests of different sizes, you can move an element from the bigger forest to the smaller one. So say you look at this forest and this one, you can move, say, this top edge to, but can you see my mouse? If you can't see my mouse, then tell me and I'll think of other ways of indicating things. So from if you look at, say, this forest, you can always, okay, so you can move, say, this top edge to the bottom one to get another element in the Metroid. So the forest form a Metroid. Okay. And to state Rota's basis conjecture, you need like one very simple property of Metroids, and that's the notion of a basis of a Metroid. So a basis is a maximal independent set. It's an independent set which isn't contained in any other independent set. So for example, in this graphic Metroid, this top row are the bases. They're the forests with 2 edges, and they're not contained in anything else. In the vector space example, the basis will be just the normal basis of the vector space. And an important property, like this kind of the basic exercise about Metroid, is to show that all bases have the same size. And this size is called the rank of the Metroid. And the way you show this is you just notice that if you have 2 bases, if you had 2 bases of different sizes, you could move an element from the bigger one to the smaller one using the augmentation property. So they can't both be maximal independent sets. Okay, so now we can state Rota's basis conjecture. It says that if you have n bases in a rank n Metroid, then you can decompose the Metroid into disjoint rainbow bases, so ones which have one element from each of the original bases. And this generalizes each of the 3 examples I had at the start. So it's an appealing conjecture because it has ties to different areas, because Metroids come up in different areas. There's lots of interesting approaches to this conjecture. In particular, you can try and prove it for special kinds of Metroids. Like if in some particular area Metroids arise, you can try and prove it for Metroids which arise in that area. And there have been results proving this for particular kinds of Metroids. So we know them for things called paving Metroids and strongly based orderable Metroids. Also, you can prove it for low-ranked matroids where Rotas Basis conjecture is a finite problem because there's only finitely many matroids of every rank, and their churn did it computationally for rank at most 4 matroids. One very important result is that Rotas conjecture is known for things called representable matroids when the rank of the matroid, this number n, is a prime number plus or minus 1. So I'll pause on this one a little bit. A representable matroid is one which comes from a vector space. So this example of basis in a vector space, that's a representable matroid. And there we know the conjecture holds for certain values of n. And I consider this to be the biggest evidence we have for the conjecture. So it's pretty unusual for math problems for them to be known for an infinite family of values like this without the conjecture being true. So how is this proved? It was proved in a combination of papers, one by Huang and Rota, and then 2 papers by Driscoll and Glynn. It wasn't a direct proof. It was a proof which involved reducing Rota's basis conjecture to a different conjecture called the Alon-Tarski conjecture. So Huang and Rota in their paper, they showed that for representable matroids, so these vector space ones, Rota's basis conjecture follows from the Alon-Tarski conjecture about Latin squares. It's not important what the Alon-Tarski conjecture is. It states that the number of even and odd Latin squares is different. But anyway, so the point is this reduction exists. And then Driscoll and Glynn, what they did is they proved the Alon-Tarski conjecture for these prime values, which then implies this result about Rota's basis conjecture. So this proof is very algebraic. And that's kind of what I mean, that because matroids can come up in different areas, there's some algebraic techniques which are relevant sometimes. Okay. So these are the kind of that's the matroids for which we know the conjecture holds. Another approach to understanding this would be to prove partial results which hold for all matroids. So let's now be in the original setting of a conjecture, you just have an n basis and an arbitrary rank n matroid, but let's try and prove weaker things than finding n disjoint rainbow bases. A natural weaker thing you can look at is, rather than getting n disjoint rainbow bases, getting less than n. Finding one rainbow basis is an exercise using the augmentation property. Basically, if you have this collection of bases, you can just pick elements from the basis one by one, and using the augmentation property, you can get a single rainbow basis. Finding more is already non-trivial, and Gillen and Webb proved that you can always find square root of n rainbow bases in the setting of the conjecture. This was improved by Dong and Gillen using a probabilistic argument, where basically they showed that if you randomly partition this matroid into n over log n sets independently, then with high probability each set will have a rainbow basis in it. And a couple of years ago with Bucic, Kwan, and Sugudikov, we improved this to about n over 2. So roughly half of what the conjecture asks for. This is one approach for partial results towards the conjecture. Another one is, so Rota's basis conjecture, it asks for a decomposition of the whole matroid into n rainbow independent sets. And you could ask, can we decompose it into more independent sets? So if you're allowed to use more than n independent sets, it should be easier. Here, the first result was proved by Aharoni and Berger, who showed that you can decompose by 2n independent sets. And a couple of years ago, there was a polymath project about Rota's basis conjecture, which was like a collaborative forum to attack the conjecture. And one of the results of that project was to improve this to 2n minus 2. So the question we'll be looking at today is an easier question of, so in Rota's basis conjecture, you basically have n independent sets and you want to cover the whole matroid with n independent sets. we'll be looking at today is if we can't prove the full conjecture, so if we can't cover all n squared elements of the matroid by n independent sets, what can we cover? So what can we prove that we can cover? And the theorem I'll present is that you can cover nearly the whole matroid using just n independent sets. So in the setting of Rotas Basis conjecture, in a general matroid, you can find n independent sets which are disjoint and cover almost all the elements. So this improves things that you would get from these earlier results. So if you look at these results about finding disjoint bases, they do let you cover a lot of elements using independent sets. So for example, this last result would let you easily cover half of the elements by n independent sets. But they're not going to give you an asymptotic result like this. And similarly, these later results about decomposing the whole matroid into independent sets, if you look at the n biggest independent sets, they'll cover also about half of the elements of the matroid. But again, they're not going to give you a decomposition. This is the first kind of asymptotic result, which holds for all matroids. And as a remark, for some special kinds of matroids, there were asymptotic results known. Notably, if you go back to representable matroids here, then these results about proving the conjecture for certain ranks. So as pointed out to me by Matthew Kwan, you can use this to prove an asymptotic version of Rotas Basis conjecture for representable matroids for all ranks. And how that works is if you have some given number n, and you have a vector space of that rank, well, you can of course embed it into a vector space of prime rank, which is a bit bigger. And by the prime number theorem, you can pick a prime which is only a little bigger than n. And because the conjecture holds for representable matroids of prime rank, this gives you an asymptotic result for representable matroids of all ranks. So for the rest of the talk, I'll give you some ideas that go into this proof, which works for arbitrary matroids. So the proof is fairly elementary. So it doesn't use any of these algebraic techniques. So right now you should see a piece of paper which I can write on. Tell me if you don't. So the proof is elementary and it doesn't really use complicated facts about matroids other than this augmentation property. So it all comes down to using kind of the defining property of matroids. So I'll spend a little bit of time now telling you about how the proof is structured, and then give you a couple of the important lemmas. So the objects that we study in the proof are, so maybe let me just tell you what the setting is. So the setting for everything I'll write now is that you have a colored matroid, which consists of n bases of size n. So you have n independent sets of size n, and you want to find rainbow independent sets. So to give you a picture of how this looks, in your head you should have this example. So you have a colored matroid. For example, here you have 4 independent sets of size 4, and you want to find a large family of rainbow independent sets. The Rota conjectures that you can find rainbow bases. You can find 4 rainbow bases, but for our theorem, we don't want to cover the whole matroid using rainbow independent sets, just most of it. So you're allowed to miss a couple of elements. So something like this would satisfy the theorem. Okay, so the kind of objects that we study are what I'll call maximum families. So maximum families of rainbow independent sets. So which I'll define as a family of n disjoint rainbow independent sets with kind of the largest total volume. So they're covering as many of the elements in the Metroid as possible. So with as many total elements as possible. And just to remind you what the theorem is, so our goal will be to show that maximum families have at least 1 minus epsilon times n squared elements. So covering almost the whole Metroid. So we'll study maximum families, and so the proof is a proof by contradiction. So we assume that maximum families have less than this many elements, and the kind of philosophy of the proof is to show that if that happens, you can move around elements in maximum families to get lots of different maximum families, and eventually we show that you can move elements around in maximum families enough that you can just find some elements from outside the maximum family to add to it in order to get a contradiction to the property that it has as many total elements as possible. That's kind of the structure of the proof. It's a proof by contradiction. What do I mean by making a family bigger? So there's like one very trivial way of making a family of disjoint rainbow independent sets bigger. Let me write it down. So I will call this a triviality because it is very easy. So say you have a maximum family, so a family of rainbow independent sets, which are disjoint and which is as big as possible in volume. Call them I1 up to IN. So this is a maximum family. Then if it really is as big as possible, then one thing that definitely can't happen is there can't be an element E, which is outside of the family, which you could add to one of these sets to get something rainbow and independent. Right, so you certainly, just by the definition of a maximum family, you can't take something outside of the family to add it to the family to get a new rainbow and independent set, because then you could just replace this member of the family by that plus the element E to get a contradiction to maximality. Just to give you a picture about what this means. So here you have a Metroid. Here you have a family of rainbow independent sets, and if this family doesn't cover everything, there'll be a remainder. So there'll be some elements which we didn't use on these independent sets. And certainly, if this is a maximum family, you shouldn't be able to add any of the elements here to any of these guys. So for example, this red guy could slot in here, and that would mean that you didn't have a maximum family to begin with. Okay. So that's an easy observation, but it already will tell us a little bit about being able to move elements around inside a maximum family. Because what this tells you is that if you have a maximum family, then any elements that you could add to these independent sets, which give rainbow independent sets, have to actually come from within the family. So any element E like this has to come from within the family. And there will exist elements E like this, because if this family doesn't cover everything, the elements in will have missing colors, right? So maybe this I1 might be missing a color. And then in that missing color, you should be able to add elements into the independent set. This comes from the augmentation property, because every color has size n. Every color is a basis of size n. These independent sets will be smaller than n. So by the augmentation property, there will be elements which you could really move like this into the independent sets to get bigger independent sets. And this observation tells us these elements have to come from within the family, so there has to be some flexibility to move around elements in maximum families. And the proof comes down to studying this flexibility. And the really key definition for the proof is the following one. The definition is of something called a K-reduced family, which is an operation which you perform on a family of disjoint rainbow independent sets. So if you have any family of disjoint rainbow independent sets, it could be a maximal family, it doesn't have to be. We define an operation called reduction. So the K-reduced family, so K is just an integer. It's denoted by Fk prime. And I'll give an example of this in a second. The definition is you start with a family, and the reduced family, you delete elements from the original family. So it'll be the original family minus some elements. What do you delete? You delete all the elements for which there are a lot of ways to move them around. So there are K sets. So these are going to be independent sets inside the family. Where basically you can do what we did here. You can move the element into any of these sets. So you could add the element to any of these sets to get something that's rainbow and independent. That's the definition of a K-reduced family. It's you delete from a family all the elements which can be moved around the family while keeping everything disjoint, rainbow, and independent. And a bit of notation, I denote Fk with a T in brackets, what you get by repeating this, iterating this operation T times on the family. So F prime, 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 T times. So the intuition of kind of how this looks, I'll give you an example, is you start with a family. Every time you reduce it, you delete some elements. So the family should be getting smaller and smaller as you do this. The proof really comes down to studying this definition and how it works. Let me now give you an example. Okay, there's a question in the chat. you look at these results we had before, these results are about packing bases, whereas this is about covering the Metroid. But maybe ask me at the end if you want to come back on that. So I think there are both packing and covering approaches to the conjecture. So yeah, so we're reducing the family. So when you reduce it a second time, all of these edges get deleted. So the twofold reduced family will just be lots of empty graphs, because here everything gets deleted. So this is the one reduced family. You could also look at the two reduced family. So you could, the two reduced family is you delete all elements for which there's at least two different independent sets to which you move it. And you can, if you look at here, you see that nothing gets deleted in this particular example, because for example, this green edge, you can move it here, or rather this light blue edge, you can move it here, but you can't move it to any of the other sets because it would violate things being rainbow. So in this case, the two reduced family is just the family itself. But the one reduced family, things get deleted a lot until you're left with nothing. So that should give you an intuition about how this definition works, and much of the proof comes down to understanding this definition. Okay. Okay, now let me tell you kind of what the goal is with this definition. So basically where the theorem comes out of this definition is the following. You prove something like the following, that essentially for any epsilon and for most values of these parameters k and t, which can come up in this definition. So there's some dependencies between k and t, but it's not going to be important what it is today. But the important thing about these parameters is that just for any sufficiently large n with respect to these parameters, you prove that if you have a maximum family, which violates the theorem we're trying to prove, so the number of elements in total is less than 1 minus epsilon times n squared. Now, the goal of studying these reduced families is to show that when you reduce a family, a maximum family in this setting, then every time you reduce it, you lose a lot of elements, which is kind of what we saw in that example. When we reduced the family, we lost a lot of elements. So we show that the number of elements in the t plus first reduction of the family is significantly less than the number of elements in the tth reduction of the family. And significantly less means you lose quadratically many elements. And this inequality, if we can prove it for this range of parameters, it gives a contradiction to the theorem. The way this implies the theorem is, so this gives a contradiction. Basically by setting this parameter t, which is the number of times you reduce, to be equal to 1 over epsilon. So why does this give a contradiction? Because then you could chain all these inequalities together for different values of t, because it would imply that the number of elements in the T plus first reduction of the family is less than the number of elements in the Tth reduction minus epsilon n squared, which is less than the number of elements in the T minus first reduction minus 2 epsilon n squared, and so on. If you just combine all the inequalities, you'll eventually get that this number should be negative, which doesn't make any sense. It's a contradiction. So we haven't really done anything yet, but I've just told you how the structure of the proof works. So the kind of goal of studying these reduced families is to show that when you do this operation, under some values of the parameters, you really lose a lot of elements always. Okay. So next, I will tell you a bit about the lemmas which we prove about this operation of reduction. I'll show you two lemmas. The first lemma I'll show you will be a variant of this trivial fact. So it'll be a strengthening of this trivial fact. Just to remind you, all this is said that if you have a maximum family, then you can't add an element from outside it to the family. And the variant will be almost exactly the same. The only difference is that this independent set will not actually come from the family itself, but it'll come from the reduced family. So let me write down what to prove. So the lemma is that if you have a maximum family, then there is no element from outside the family which you can add to an independent set to get something that's rainbow and independent. So if you just compare it to what this trivial observation was, so far it's almost exactly the same. So if you have a maximum family, then there is no element which you can add to an independent set to get something rainbow independent. Before this independent set was in the family, now we say that that the independent set is in the reduced family. Okay, so that's the difference. And this lemma is stronger than the trivial observation we had before because the reduced family always has less elements than the original family because things get deleted when you reduce. So that's why this is stronger. So just like if the reduced family has less elements, that means that the independent sets in it are smaller. So there should be more elements which you can add to independent sets to get things that are rainbow and independent. And also, just as a remark, there's some dependence on the parameters here. So for this lemma to hold, you need that this k is bigger than 3 to the t. Let me see if I have time to prove this. Okay, let's try and prove it. So I'll just give you the proof for t equals to 1. So it'll have the ideas of the main proof here. So for t equals to 1, so we have an independent set inside this reduced family. And it'll just be the one reduced family. So we have this independent set in the one reduced family. And so this independent set has to be contained inside some independent set in the original family. It's contained in some independent set J in the original family. So all that's going on here, just going back to the picture, is so this was the original family, this is the reduced family, and there's a natural containment between independent sets in the reduced family and the ones in the original family. Okay, so we know that the element E, when you add it to this independent set, it gives something that's rainbow and independent, but it's not the case that if you add it to J, you get something that's rainbow and independent. You might create some dependencies. But what you can do is you could add E to J and remove two elements to get something that's rainbow independent. So there exist two elements, F1 and F2, in J minus I, with J minus F1 minus F2 plus E rainbow and independent. So this is something that just holds in general. So if you have any rainbow independent set J and any element E, you can always add E to J and delete two elements to get something that's rainbow independent. How does this work? Well, when you add E to J, there might be one element in J which uses the same color as E because J itself is rainbow. So let's delete the element. So F could use the same color as E. And then now J minus F1 plus E will be rainbow, but it might not be independent. But similarly, when you add E to J, you'll create at most one dependency, and you can delete one element to get something that's independent. So you need to only delete two elements to get something that's rainbow and independent. Okay, but these elements F1 and F2, they are not contained in I. They're not contained in the set which is in the reduced family. So here we can use the definition of the reduced family. The definition of the reduced family which is like here. It tells you that there's K, so this element so we'll apply it when this E here is the F1 and the F2 because they're not in I. So it tells you that there has to be K choices of independent sets I1 and I2 with when you add F1 to I1 and add F2 to I2, you get rainbow and independent sets. So this is just this definition or this definition. Okay, so now let's draw a picture. So you have this element E. Oh no, sorry. You've got this element E. We know that when you add it to J, you can delete two elements, F1 and F2, to get that when you move this, you delete these two, you get something rainbow independent. But for both of these elements, we have two places where we can move them, such that if you move F1 here and F2 here, you get something that's rainbow independent. And if you perform all three moves together, you'll increase the size of your family by one because you move two elements which don't change the size of the family, and you've added one element which came from outside of the family. So you've increased the size of the family, which contradicts maximality. So that's the proof of the lemma for t equals 1. For higher t, it's very similar to this. The difference is it's kind of an induction. So for higher t, when you move these two elements to these two sets, you won't get something that's immediately rainbow independent, but you'll instead need to find more elements here, which you further move out to some new set. Oh, sorry. And it's kind of an induction based on that. Okay. Okay, so this is the first property we prove about reduced families, that this generalization of this trivial fact about maximum families still holds. Remember, the goal which we're striving towards is to prove something about how many elements are lost when you reduce the family. So the next time I'll show you, we'll say something about how many elements reduced families have. The next lemma will be, wait, am I supposed to finish at 50 minutes, right? Yeah, right. So sorry. Yeah, sorry. I should probably finish now. Then
so I think you can talk a couple minutes more. Just leave at least 5 minutes.
Yeah, maybe I'll show you the lemma. Where is it? I think I'll go on to open problems now. So using this lemma we just proved, you can use it to give bounds on how many elements you lose when you reduce. But it does take a little bit of work to get there. So let me go on to some open problems. So I think there's a number of open problems about proving better asymptotic versions of the conjecture. You kind of try and improve the bounds you get. So the bounds that the proof we have gives are n over root of log n. And to be honest, I didn't try improving it at all. So it would be very interesting to get like a polynomial bound here. And also you can try and prove better qualitative versions of the conjecture. So for example, on one of my slides, I mentioned the approach of finding lots of disjoint bases, and you can try and prove a better asymptotic version using that approach, or this Aharoni-Berger approach of covering the whole Metroid by independent sets. And again, we don't have an asymptotic version there. So I think all of these are interesting directions, and it will be interesting to try and improve the proof to get things like this. Okay, I'll stop there. Thank you very much.
Please thank the speaker. If you clap in your hands right now, we can't hear you because you're muted. So do we have any questions for Alexey?
So there's one on the chat from Rota about a partial Latin square result approach. What do you mean by the partial Latin square approach?
Oh, hi. So for the partial Latin square, it's if you look at the col, if you take the rows as a matrix, the columns also form a basis, and then the set of our element sets has the property of the basis of Metroid.
Yeah. So do you mean kind of
Then,
like we had on this earlier slide that the rows here are bases, and you're looking for the columns to be bases, or you think it's something else?
yeah, it just a different approach, because you can check the relationship of the columns to check whether they're in the 2 points are independent or not.
I'm still not sure what. Are you referring to this result of like Juan Rota and just go, this uses Latin squares? Do you mean that approach?
Yes, that's let me see. Is Henry Kroppel has some results about this.
Who does? Can you type it in the chat?
Yeah, let me type here. So yeah, actually,
interesting,
a thing that's for Latin square, according to the order, is whether it's odd or even. There are two different results.
So
Yeah,
I'm not aware of this result, so I'm gonna Google it after this talk and see if what the
yeah, I think
relationship
it's
is.
a
But
mostly algebraic approach.
it sounds like maybe it's related to this how these representable Metroids work, but I could be wrong. But yeah, it's interesting. I'll check it out. Good question.
Okay, thank you.
So this one. So Alexey, it seems like by allowing to have the system not perfect, not complete, you have a little bit of freedom. And can you get algorithmic results, not just show that there exists something, but provide the construction which
Yeah, so construction for a
provides
family,
this non-zero probability.
for a family like this. Let me think. So I mean, it's sort of constructive in that.
Yeah, the argument seems to be constructive.
Well, I'm not sure how efficient it is. That's the thing, because like you move around these elements through the basis quite a lot, so I'm not entirely sure it's efficient in any sense. But I haven't thought about that. So it's definitely somewhat algorithmic in that at least it doesn't use any like probability or anything. So in that sense, it's algorithmic. Like, I'm not sure whether it gives like a polynomial time algorithm for finding this family. It's a good question.
It's a separate question how to make it fast. But
yeah, it definitely gives an algorithm, but yeah, I don't know how fast it is.